Lesson 9.2, Magnetic Force on a Moving Charge. Since currents, which are moving charges, make magnetic fields, then other magnetic fields apply a force to moving charges. For a moving charge to experience a force, the charge must be moving, and the velocity vector of the charge must have a component perpendicular to the magnetic field. In other words, the force on the moving charge is the size of the charge times the velocity vector cross product with the magnetic field vector. Now we haven't done cross products yet, and probably, so we can simplify it as charge times the velocity times the magnetic field times sine of the angle, where the angle is the angle between the velocity and the magnetic field vectors. The direction of the force on a positive moving charge can be given by the right-hand rule. For a right-hand rule, the fingers point in the direction of the magnetic field, the thumb points in the direction of the moving charge, and the palm faces the direction of the force on a positive charge. If the charge happens to be negative, it would go the exact opposite direction. For example, here your fingers would go the direction of the magnetic field. Your thumb is going to point the direction of the V, and then the palm is going to point the direction of the force. The force will be zero if the velocity and the magnetic field vectors are parallel. So the moving charge would then be unaffected if they're going parallel to each other. In order to be affected, there has to be a component perpendicular to the magnetic field. So what would be the motion of a charged particle in a uniform magnetic field? Turns out it's circular. The force is QVB sine theta. But if it goes in a circle, then that force would be the force that makes it go in the circle. So that would be the centripetal force. So we can make those equal to each other. We can cancel out one of the V's. Let's say we're perpendicular, so that's 90. Sine of 90 is 1. And then you could solve for R, mv over qb. If we take a look here, when the vector is an x, that's the feathers of the arrow. You know, an arrow has a tip, but at the end it has these feathers. So when it's going away from you, you see the feathers. If it's coming towards you, you see the tip. We call that out of the paper. X will call into the paper. So in our diagram here, the magnetic field is all X's, so it's pointing into the paper. So you can see the fingers of the right hand point into the paper. At the bottom, the particle is moving towards the right. So the force must be going up. When you get to position 2, the fingers are going away into the paper. Your thumb would be pointing up, so the force would be going towards the left. And so it just keeps bending around. That force keeps going towards the center of the circle, which causes the particle to change direction and go in a circular path. Here is a picture of different charged particles. This is from a bubble chamber. And you can see they curl around in circles and spirals. It can be used to determine the relative mass to speed and charge ratios of the particles. So you can see this one here, particle 3, has a very large radius. That means it's going very fast. Whereas particle 1 and 2 are much smaller radiuses. They're not going as fast. Another application is a mass spectrometer, which an ion source shoots particles into a magnetic field, which causes them to turn and curve. And then there's these detectors. The detectors count how many particles of that end up in there. But this radius, all the ions are shot with the same speed, so the difference in the radius is due to their mass. So a smaller radius would be a smaller mass. Bigger radius would be a bigger mass. And by doing that, you can determine the different masses, and you can figure out the composition of some unknown material that you are studying. A particle with a charge of negative 1.6 times 10 to the negative 19 coulombs and a mass of 9.11 times 10 to the negative 31 kilograms. What's that? It's an electron. Moves along the positive x-axis from left to right. It enters a 3 Tesla magnetic field in the xy plane and points 45 degrees above the positive x-axis. So my magnetic field is going like that, where this is 45 degrees. What is the direction of the force on the particle? Well, we'd use our right-hand rule. Fingers would point that way. Thumb's going to point that way, which means our force is going to come out of our palm, so it's going to come that way, straight up at us out of the paper. Well, this is X and this is Y. Straight up out of the paper is Z. So we could say it's the positive Z direction. Except for it's not going to be positive because our charge is negative. So that gives us the force on a positive charge, but this one's not positive. This one is negative, so it's going the opposite direction. So instead of out of the paper, it'll be into the paper. And it's the opposite direction because it's negative. After it's been in the magnetic field, the particle moves in a circle. If the radius of its path is that, what is the speed of the particle? Okay, so R equals mv over qb. I know the R. I know the m. We are looking for the V, the Q, and the B. So probably let's multiply both sides by the denominator. So I get negative 9.6. It's 10 to the negative 29. Meter Coulomb Teslas equals the 9.11 times 10 to the negative 31 kilograms times V. So we'll divide. and I get 105 meters per second for the speed. Lastly, what is the magnitude of the force on the particle? Well, force is QVB sine theta. So our charge, oh yeah, what happened to my negative before? Well, we want the magnitudes here. What is the speed? We want the magnitudes. We're not worrying about our direction. Again, on this force, I want the magnitude, so I'm not going to worry about the direction. And our angle is 45 degrees. Put that in the calculator. And I get 3.58 times 10 to the negative 17 newtons. Well, this is a very large force, but it's a very small particle, so it does have effect on it.